Hi, in the previous video we saw a simple explanation about the buck converter and we obtained the expression of the output voltage as a function of duty cycle and input voltage. That explanation is very good as a first approach to understand the buck converter, but if we want to analyze other DC to DC converters we need a different tool. So in this video we will see a systematic approach to obtain the output voltage expression of different DC to DC converters. We will see the method and we will apply it to the buck converter, and let's see if we obtain the same output voltage expression. Well, so before we apply the method, we must take into account some points. First of all, we will assume that our components are ideal devices. So as a consequence, we don't have parasitic elements and the power consumed in those devices is zero. The second point that we have to consider is that we work under steady state conditions. What is the meaning of that? When we turn on a DC to DC converter, capacitors and inductors are discharged. It means that the voltage across a capacitor is zero and the current through an inductor is zero. But after some switching periods, those voltages and currents will change, and after some time we will have the final scenario where those waveforms are constant or at least periodic. As an example, here we can see a possible evolution of the capacitor voltage. Here we have the turn on of the DC to DC converter. We have 0 volts. We have a transition, okay, and after that we have steady state conditions, okay. So in that part the waveform is constant or periodic. As you can see, if we see here the switching period, we notice that we need a couple of or some switching periods in order to reach steady state conditions. But well, the point is the method that we are going to see is valid for steady state conditions, is valid for this part of the waveform. It's not a problem because initially when one of the most important things that we need to know when we start studying power electronics is the operation of converters in steady state conditions. The initial transition of the turn on is something, let's say, for advanced topics. Well, so last comment about that is that in the following figures, when I put t equal to 0, it doesn't mean that I turn on my DC to DC converter at this point, okay? I will consider that t equal to 0 is already in steady state conditions. What are the consequences of operating under steady state conditions? We will have two consequences that we will use in the method. First of all, we will consider the voltage across a capacitor. If we are in steady state conditions, that voltage is constant or periodic, as in this case. If we have a periodic voltage or constant, the voltage at the end of the period is equal to the voltage at the beginning of the period. So it means that this voltage is equal to this one. Okay? Now let's apply the general expression of the voltage across a capacitor and we will impose this condition. So we can say that the voltage across a capacitor at the end of the period is equal to the voltage across the capacitor at the beginning of the period plus 1 over C, 1 over the capacitance, integral of the capacitor current between 0 and the end of the period. If we say that this voltage is equal to this one, this part must be 0. So in this way, we can say that in steady state conditions, the average current through capacitors is 0. This principle is very important and is known as capacitor charge balance. Well, second consequence of operating under steady state conditions. The current through inductors is constant or periodic, as in this case. It means that at the end of the period, the current through an inductor is equal to the current that we have at the beginning of the period. Basically, this current is equal to this one. Let's apply the general equation or general expression of the current through an inductor. The current at the end of the period is equal to the current at the beginning of the period, plus 1 over the inductance integral of the voltage across the inductor over a period. If this path is equal to this path must be 0. So in steady state conditions, we can say that the average voltage across an inductor is 0. This principle is also very important, we will use it today, and is called inductor volt-second balance. Third point that we have to consider, we will consider that the capacitance of the capacitor is a very high value. In general, the voltage across the capacitor in DC to DC converters is something like this. Okay, we have an average value that I will note as capital V C, and then we have some ripple, some AC component. We define the voltage ripple as in this way. Sorry. Basically, it's the peak-to-peak value. And one point that we must take into account is that if we increase the capacitance, the ripple falls. Okay, we get a smaller value, we get a more constant voltage across the capacitor. So we will consider that the capacitance of the capacitor is so large that the voltage ripple is negligible. In this way, we will consider that the voltage across capacitors are constant values. So Vc is equal to capital V C, the average value. Similar idea, the inductance of the inductor is so large that we will neglect the current ripple. Let's see the explanation. In general, the current through an inductor is something like this. We have an average value that I will note as capital IL and some ripple. In this case, the peak-to-peak current ripple is this part of the waveform. The thing is, if we increase the inductance, the peak-to-peak ripple falls and we get a more constant value. So we will assume that the inductance is so large that the ripple is negligible and we have a constant current through the inductor. Okay, so my inductor current is a constant value that I call it capital IL. Well, so if we take into account these points, we know the limitations of the method that we are going to see, or at least we know when we can apply our method. So now let's see the method and let's apply it to the buck converter. The method is very simple. We only have 2 steps. In the first step, we evaluate the voltage across the inductor over a switching period. And in the second step, we apply the inductor volt-second balance in order to obtain the output voltage expression. Okay, so let's apply this method to the buck. Here we can see the topology on the left side and the control signal of switch A on the right side. As you can see, the control signal is a periodic signal, the period is the switching period, T switch, and we keep the switch on during D times T switch. Remember that D is the duty cycle. So the target is to evaluate the voltage across the inductor over a switching period. This is the first step of the method. In order to evaluate that voltage, what we are going to do is to establish two states. First step or first state is this one. This is state 1, is from 0 to D times T switch, and second state is this one, from D T switch to T switch. So we will consider state 1, state 2, and we will evaluate the voltage across the inductor in each state. So in the first state, in this part, what we know is that switch A is on. So here we can put a short circuit. As a consequence, the voltage here is VI. In this way, diode SV is blocking VI, so the diode is off. We can put here an open circuit. Well, so now we can try to obtain the expression of the of the voltage across the inductor in this state. In order to do that, I will apply the Kirchhoff voltage law. I will follow this path and we will express the inductor voltage as a function of VI and VO. So we can say that the voltage across the inductor is plus VI minus VO during state 1. Note that this voltage is constant in this interval because VI is constant and VO is constant. Let's see what happens in state number 2, this part. So what we know is that in state 2, switch A is off. So here we can put an open circuit. What happens with switch V? Switch V is a diode. The answer is that switch V is on. The explanation will be given at the end of the video. So now you have to trust in me. So let's consider that in state number 2, the diode is on. Okay? In this way, this voltage is 0 and we will repeat the process. I will evaluate VL applying the Kirchhoff voltage law, following this path, and we can say that that voltage in this state is 0 minus VO. So basically we have minus VO. Again, the voltage across the inductor is constant. It's a different value in comparison to state number 1, but it's constant because VO is constant. So now we know the voltage across the inductor in state 1 and state 2. Let's draw the waveform. So as you can see, in state 1, we have VI minus VO from t equal to 0 to D times T switch. This is state 1. And in state 2, which is from D equal to T switch to T switch, we have minus VO. Now let's apply the second step of the method. Apply the volt second balance to inductor L. So essentially we say that the integral from 0 to the end of the period of the voltage across the inductor must be 0. This integral is very easy because basically the voltage across the inductor is a set of constant values. We have a constant value here, and we have another constant value here. In this way, we can split the integral in two parts. One is from 0 to d times t switch, where we have vi minus vo, and the second one is from d times t switch to t switch, and here we have minus vo, and we know that it must be equal to 0. Okay, let's solve this expression. It's very easy. It's vi minus vo times d times t switch plus minus vo times 1 minus d times t switch, and it must be equal to 0. Note that this part or the length of interval 2 of state 2 is 1 minus d times t switch, because interval 1 is from 0 to d t switch, and interval 2 is from d t switch to t switch. If we solve this expression, okay, we obtain the final expression of the output voltage. Vo is equal to d times Vi, which is the same expression that we obtained in the previous video. Well, one comment here. Essentially, when we apply the volt-seconds balance, what we say is that the area of this positive path is equal to the area of this negative path. Okay, we can do it in this way, or we can do it working with the expressions, but the result is the same. Well, finally, before we finish, we have to answer this question: why the diode is turned on when we turn off the MOSFET? In order to get the answer, we will analyze this node. In this node, we can see three currents. We have the inductor current, we have the output current, and we have the capacitor current. In this way, we can say that the inductor current, applying the Kirchhoff current law here in this node, we can say that the inductor current is I0 plus IC. Well, I0 is VO divided by the resistance. Here we take into account the Ohm's law. So if VO is constant and the resistance is constant, the output current is also constant. I will use this notation, capital I-O. Okay, now let's consider one of the points that we assume for applying the method. The inductor current is constant. Remember that we consider that the inductance is very high, so we don't have ripple. So let's consider these two equations here. We can put that first expression in this way. And now let's consider one more thing. In a steady state, the average current through a capacitor is 0. So now let's consider this expression, the previous expression. This value is constant, this value is constant, and this part, we don't know if it's constant or is variable, but we know that the average value is 0. So in this way, it's pure AC, it's pure variable. So if this part is constant, if this part is constant, and this part is pure AC, the conclusion is that the current through the capacitor, according to this explanation of this video, is 0. Well, In summary, for this explanation, the important thing is that the current through the inductor is constant, is equal to the output current, and it flows from the left side to the right side. So now, if we know that we have that current, let's consider what happens when we turn off the switch A. So, in the transition from state 1 to state 2, we turn off this switch. Before that, the inductor current was flowing in this way. But when we open the switch, we need a new path for the inductor current, because as we can see here, the value of that current is constant. So the new path of that inductor current is the diode. In this way, the inductor current forces the diode to be on when we turn off the switch A, the MOSFET. Okay, well, so I think that with this, we finish with the scope of this video. We have seen a general method to obtain the output voltage expression in a DC to DC converter. We apply it to a buck converter and we obtain the same expression of the previous video. But we have more questions to address in future videos. We need to see what is the relationship between the inductor current, and in particular with the current ripple through the inductor and parameters of the circuit. We have to see what is the expression of the output voltage ripple, that here we consider that was 0, and other questions such as what is the consequence of considering components with some parasitic elements. So we will see those points in future videos, but for today we have finished. So thank you for watching this video and see you in future videos.